So, here we are on our third week run, and today we are approaching or rather entering the fascinating land of the Ito calculus or the Ito integral. Ito is a name of a Japanese scientist who introduced this, and with that he changed many things in physics. His things changed many things in physics and also in probability, and Ito integrals and the calculus associated with it, the Ito calculus, is the key to doing a lot of computing or solving a lot of models in finance. So, this is the holy grail of stochastic calculus, and we are going to do it step by step. We are not going to be in a hurry, we are not going to push ourselves into too much of rigor. Of course, rigor is a necessary tool of a mathematician, but looking at the diverse audience that I have, you cannot push rigor too much, but I will try to get you some understanding. And in this whole the remaining part of the course, the book I will follow a single book, which is one of my favorite books in mathematical finance. It is called Stochastic Calculus for Finance. So, this book is written by Stephen Shreve, a very famous name in mathematical finance from Carnegie Mellon University. I have taught from this book earlier, and this is my favorite book in this subject. I would rather like to show it. This is the book, and the interesting part is that this book now is an Indian edition, both the volumes. This is volume 2 from which I am teaching. So, volume 1 and 2, there are 2 volumes. Volume 1 talks about discrete time, here we are talking about continuous time, and both these books are very lovely read, and those who are serious about mathematical finance should actually procure the copy of these 2 books. This will be helpful in many ways, and this book takes you from a very basic to pretty advanced level. So, now what we are going to do in this section, we are trying to make sense of the term, sense of this. Of course, you might ask what is DWT? You just said in the last class that this Brownian motion is not differentiable anywhere. Yes, but assume that this is like writing the difference, this is the increment of the Brownian motion, we had been talking about increments of the Brownian motion. So, we want to, so the question is, can we make sense of this? And what is this delta t? Delta t is a process adapted to the filtration Ft associated with the Brownian motion. So, just like in standard integration theory, we will start by trying to look into the meaning of this when this process is nothing but step functions. At every t it is some step function, on a particular interval it will hold a particular value, fixed value. So, our job would be now to make, you will see that finally when we will compute things, you will see that this will give us a very different answer than standard calculus. It is the quadratic variation of the Brownian motion that would be the culprit. So, here again we are going to partition 0t into intervals. So, here we are partitioning where you have this Now, we will talk about a simple process or a simple function basically. We will take this to be a simple process. Simple process means on each interval Tj to Tj plus 1, right, which includes Tj and not Tj plus 1, this is constant. So, basically you are looking at a function of this form. So, here is your 0 to t, here is t1, here is t2, here is t3, say I will just do it 5, t4, t5 and this is t6. So, what you are expecting that from 0, suppose this to here you have some particular value, then t1, so here you do not have the value, this value is not valid here, it starts again from here, t1 to t2, that is why we are giving this round, this is one particular value, then t2 to t3 it could be like this, t3 to t4 it could be like this, t4 to t5 it could be this one, and t5 to t6 it could be like this, just as an example. This is a step function basically, and this is an example of a simple process. So, this is one sample path of that simple process, right. So, on this thing, if this is the way you have broken it up, the partition, on each partition we will consider that it is constant. Of course, if you take more smaller partitions, the same idea will remain fixed, okay, there will be two intervals where you will have the same value. Now, given this partition on which it is constant, so we will look at only those intervals on which it is constant and that will partition the interval. We will try to calculate it. Now, by delta t, let us work like a financial guy. Let us think delta t is the position I am taking in an asset at time t, that is delta like a stock. So, delta t is the number of stocks I am holding at time t of some company for example. So, number of stocks I am holding at time t. Now, let us now assume that Wt, the Brownian motion, just like as Bachelier thought, describes the price process of the stock. But you know that this is really not true, because price process of stocks never take negative values while Brownian motion can. But for the moment, just for the heck of it, think that we are in Bachelier's days, we are not bothering of those things, and we are talking about the fact that Wt is the price. So, what I have done, so at time t, what is my gain in trading at time t? So, IT is the gain, is a process, is actually a stochastic process describing the gain by trading at time t. Now, consider the inter t which is lying between t1 and t0, right. Now, I have actually bought say delta T naught quantity of objects at time T naught, and for which I have paid W T naught as the price. So, W T naught is the price per unit, of course. So, my total money I paid, so let me write IT. So, what is IT in this case? So, total money I paid to get this delta T naught amount of stocks at T0 is WT0, and total money now I take hold on to the stock at time T, at a time T I sell that number of stocks and at a price WT, because price is changing at every time. So, by selling those stocks I make this amount of money. So, what is my gain? Gain is nothing but the difference of these two, amount of money I spent and then amount of money I actually bought by selling. So, I will just subtract these two to know whether I am at a profit or loss. Gain could be negative also. Now, think that what would happen if my T is between T2, what would happen to this? What would happen to this scenario, right? So, what would be IT when I am in that particular scenario? In that case, of course, T naught is in this case 0, so you can write delta 0 also here, does not matter. So, when I am writing this T here, one has to be very careful, I am meaning that I am ending the trading at this time. So, what happens when I am telling the T is between T1 and T2, because which means I have held to the stock WT naught up to the time T1. After that I will change it. So, at time T1 I sell my stock which I bought this amount of stock at time 0 with the price WT1. Then I bought a stock with this money that I have got. I have bought a stock WT1 delta T1 at time T1 paying price WT1. Then at T2 at time capital T, which is lying between T1 and T2, I sell this WT1 holding, delta T1 holding. So, delta T1 to WT. So, by selling I totally gain this amount, and this is the amount I have spent to actually buy the delta T1 stocks. So, it will be this minus this. So, which I can also write nicely as IT in this particular case, IT is delta 0 WT1 plus delta T1 WT minus WT1. Again, if you are slightly not comfortable, what I did, I know that my maximum time I can hold the stock I bought at time 0 is up to time T1, then I have to sell it, that is the period of holding. Then at time T1 I know what is the stock price and I sell it with this price. Now, with that price I buy stocks WT1, stock of the amount delta T1 with the price WT1. So, this is the amount now, this amount now has to be subtracted from this one, because I sold and got some money, from that I spent some money to buy some new stocks. Again I sold those stocks at time capital T and I finished my trading, time small t and I finished my trading, I got this amount of money. So, this minus this plus this is the amount of money I have now. So, this is a very simple thing. Now, this can be written in a more general way, that if T, so if you have a T lying between Tk and Tk plus 1, then your IT So, this is what does it say? Say at every time point before the time till time k minus 1, what did he do? He bought something, he holds something in one interval, then sold that thing and bought the new stock by using the money from the same thing that he had gained. He sold something, whatever money he had got, he spent a part of it to buy something. So, he held this stock up to time Tj plus 1 and sold this at this amount. But at time Tj he had at time Tj he had bought the same amount by spending the money delta Tj into WTj. And then of course if you look at the last part here, the same this into this whole thing into W T minus W Tk. So, this is the general form of writing IT. If you are not comfortable with or can't see it, I write it again here for your convenience. It is very simple profit and loss thing. I trade, make money, use that money to buy something, again I sell that and buy some new thing. So, that's the whole thing, that is the whole idea, that is the way the market actually operates. This IT so this IT is often written as I0 to small t. So, this whole thing is written in a shorthand like this, that is how we give meaning to this thing. So, this is what we want to write as dWt, it is a shorthand writing, it is not exactly the differential, there is nothing like a differential of Brownian motion, it is a shorthand writing. Now, IT then itself is a stochastic process. So, IT is called the Ito integral of the simple process delta t. So, IT is called the Ito integral of the process delta t. So, you are taking Ito integral of a stochastic process, that is very important. And it is not like integrating a random variable, integrating random variable is just like integrating any function, right, that is. So, here what you create is also a stochastic process. Your integral itself is not a number, but your integral itself is also a stochastic process. IT is a stochastic process. So, you see there is a huge leap or huge difference in the thought process. So, when you come to the stochastic world, your life completely changes. Now, what are the key properties of this stochastic process? The key properties are following. The number one property is that the Ito integral properties, if you have time we will prove any one of them. The number one property is that Ito integral is a martingale with respect to the filtration Ft adapted to the Brownian motion W. The Ito integral is a martingale. Ito integral. So, when I am taking integral, do not think it is an integration, it is a number, it is not a definite integral. Ito integral IT means Ito integral is a stochastic process, Ito integral IT is a martingale. Martingale are essentially processes which possibly are trying to maintain status quo at every time. Number 2, proving this is not so simple. It needs little bit of work, but nothing else, it is just the computation is complex. Another thing is called Ito isometry. We will see what is the meaning of Ito isometry. Ito isometry says the following. Expectation of I square t, so expectation of the random variable I square t squared is equal to expectation of 0 to t delta square u du. Now, why it is called isometry would be clear if you only know something about L2 norms. See, look at this quantity E I square t. So, if I write here as E I square t, this simply means integral, right, whatever is 0 to t, integral over not 0 to t, integral over sample space, whatever the sample space is, of I square t dp. So, this because you are assuming that this is finite, I am assuming that this is finite. So, once you assume that this is finite, you are assuming that I square t actually belongs to the capital L2 of L2 space of, this is only for those who know this stuff, this function analysis. Those who don't bother, think that Ito devised this formula. Isometry means they have similar distances. So, distance in the original space between 2 points and distance in the range space between the two functional values are similar, then we call it isometry. So, this actually means if you look at it very carefully, it is, if you take I, no sorry not I, IT is in L2 FP, not I square. So, I t, this is the square of the L2 norm. So, this is nothing but the square of the L2 norm. So, this is I2 is in infinite dimensional space in this, IT itself is an infinite. So, the Ito integral itself is an element of L2. So, it is in the infinite dimensional space, it is an infinite dimensional object. So, it is so interesting, things are coming in. And if you look at this, so they are telling that this is expectation of this. So, you are telling that the distance, the norm of this is computed is nothing but the expected value of this integral, because this integral, if you take the expected value of this integral means what? This is a normal integral, this is a standard Lebesgue integration, right. Here I am not treating delta square as a function of omega basically, keeping the u fixed, but I am treating it as a function of u itself. So, for every sample path you can compute this, as t changes, fix up the sample path, sample the scenario omega, and you can compute this, and then you take expectation over all the sample path, average over all the sample path. That is exactly same as the norm of L2 norm of this, that is the idea. Now comes a very important property. So here all these things are been done for the Ito integral for the simple process delta t. We have not spoken about Ito integral for a general case, and that we will come tomorrow in the next or in the next class. The very important thing that we should now understand, that just like Brownian motion, the Ito integral itself has a quadratic variation. And what is that quadratic variation? So Ito integral does not have a 0 quadratic variation, Ito integral itself has a quadratic variation. The Ito integral states the quadratic variation of the Ito integral is being given by this simple thing. It is amazing, the answer. So the Ito isometry says the following: that the L2 norm of I, the integral, is nothing but the expectation of the quadratic variation. See, the quadratic variation itself, whether it is of a Brownian motion or whether of this integral itself, is a stochastic process. That is the thing that you have to take into account. The quadratic variation, but it is very interesting, the quadratic variation is a stochastic process, but for every t it gives you a number. Every t it is a fixed number. For a given sample path, for every omega it will calculate a number very nicely. So for every omega, whatever be your path, for a given t, therefore whatever be your omega, this will be the answer. So it is path independent essentially. So the quadratic variation itself is a stochastic process. So what we have learned is completely for the case where delta t is that simple function, that is all, delta t is this. So I know that delta t, given the t, delta t varies like this. So given any omega, if it is in the time interval this, delta t will have these values, that is all. It does not depend on what omega. Right. So delta t is the simplest function. So delta t I made a mistake. So given an omega, delta t will take these values in this interval. You change the omega, it will take some other values in these fixed intervals. So the intervals are fixed, and in those intervals it is taking constant value, but it will depend on the omega. So you change the omega, you will have different values. So and that omega will change the value of it. So that making it a stochastic process. Similarly, this quadratic variation itself is a stochastic process. So this is a very important understanding, that we are essentially generating not numbers, we are at every step generating quadratic stochastic processes. So this is something of very important thing that we have to keep in mind. So when we are going to talk about general integrand, when this is some adapted process, delta t is an adapted process, not a simple process like this, that is not step function type thing, then we proceed as we do in integration theory. We write we approximate the given function delta t in as a we approximate it by a family of simple processes, simple functions, and then you take the integral over those simple functions and then take the limit. That is the idea we are going to apply, and then we will see for one particular calculation what will happen. And there is a, so we had learnt in the last class that the quadratic variation of course people should ask what is the, when we take the limits of those q pi, what sort of limit it was. We proved that what the limit we get is a limit in, or the convergence that we get, that we can always have convergence in probability, but under slight mod, and also if we just bother about the fact that the variance is the variance is 0 and the expectation is t, then we have something called L2 convergence, which I am not going to bother you with, or else by slightly modifying the definition, by slightly modifying the requirements or the behavior of the partition, we can show that it can be made to be convergent almost surely. So you just have to remember this, but remember this is also a process, stochastic process. Sometimes now, because we have started using this DWT symbol, we will use this shorthand. This actually means quadratic variation. This is the meaning of this. We will this is nothing but these two differences, right? The difference square basically. So we will use this shorthand. Please note that this whole thing is a shorthand to write quadratic variation, but this shorthand would be very helpful when we do finance, very extremely helpful to use this shorthand. So thank you, and tomorrow we are going to talk about some more interesting facts, doing Ito integral for a general integral, and all these properties that you have learnt here would be actually translated to that general integral, and then we will do an example.